This is Radio Ecoshock with Alex Smith.
Welcome to Radio Ecoshock, this week packed with urgent climate science. Dr. David McKay says we are approaching multiple tipping points. It may be the most important warning of the year. Professor Rob Jackson from Stanford, chair of the Global Carbon Project, explains why controlling methane is our best chance for a livable climate. NCAR senior scientist Kevin Trenberth returns to explain the basis of it all, Earth-energy imbalance. Let's go. Scientists reach new conclusions about climate tipping points. YouTuber Simon Clark calls it the scariest paper I've ever read. From ocean currents to Arctic ice, the workings of this planet are not as stable as we think. 16 giant Earth systems can switch from one state to another at temperatures close to present day. Everybody needs to get this. The new paper is titled, Exceeding 1.5 degrees C Global Warming Could Trigger Multiple Climate Tipping Points. The lead author, David McKay. He is research consultant and science communicator from Georesilience Analytics. David is also associated with the University of Exeter and Stockholm Resilience Centre. From Brighton, England, David McKay, welcome to Radio Ecoshock. In 2008, I interviewed Dr. Tim Lenton from Exeter, who you know very well, about the science of cascading tipping points. But first, let's outline our terms. What is a tipping point, and how is that different from a tipping element?
So in this study, we use a definition of climate tipping points. That's quite specific to try and clear up some of the confusion that's been out there in the literature and the media. So we focus on this aspect of self-sustaining change. So we say that a climate tipping point occurs when, in part of the climate systems, that's something like an ice sheet, an ocean current, a rainforest, when change in that system becomes self-sustaining beyond some warming threshold. And that's normally the result of some sort of positive amplifying feedback process, kind of leading to a runaway change in that system. And the tipping element is the part of the climate system the tipping point happens in. So the element is, for example, something like the Greenland ice sheet, and the tipping point is the threshold beyond which the Greenland ice sheet will collapse without being able to come back to its previous state.
David, why do you think the science of tipping points is rising to top of agenda here?
I think it's because there's been so much science that's happened over the last 15 years since it was first introduced in this 2008 paper that Tim did. Back then, it was a thing that could potentially happen at some of the higher temperature levels. So a lot of the tipping elements they identify there happen in the sort of 3 to 5 degrees above the level of warming in the 90s. So it sort of felt like kind of a far-off possibility. But in the 15 years since then, climate science has only really kind of brought those thresholds down and added new potential tipping elements as well. And now that it's coming to the point of being in some of those tipping elements are now possible to be triggered now, even at today's level of warming, and we can see that warming is going to get to at least 1.5 degrees in the coming decades. It's all becoming too close to home for comfort.
When the Arctic sea ice suddenly shrunk in 2007, scientists in the field were blown away. Was that a tipping point seen in the rear view mirror?
So in this study, we don't talk about Arctic summer sea ice as being a tipping point, which is probably something that might be a bit controversial amongst some listeners, because that's traditionally been one of the sort of classic tipping points that people have talked about, or the stuff to do with the albedo positive feedback loop. It was a really good example. But in this study, we don't actually include summer sea ice as a tipping element. And that's because in the literature since 2008, we just couldn't identify a particular threshold beyond which the change in the Arctic sea ice became self-perpetuating. So there was a big low in 2007 and some big lows since then in the Arctic summer sea ice. But in general, it's somewhat rebounded afterwards, and it's following a logistic curve downwards.
Picking up on when you say it follows a logistic curve downward, because the public perceives global warming and its impacts as rising a bit every year and every decade. But are more sudden changes of state possible?
Yes, exactly. And for example, with Arctic winter sea ice, from various different model into comparisons, we can see that there is actually the possibility for abrupt changes in Arctic winter sea ice as a result of this sort of self-sustaining change that comes out in the models. That happens at a higher level of warming than Arctic summer sea ice. But certainly there are parts of the system where we do see these more abrupt shifts driven by these tipping dynamics. Whereas we think Arctic summer sea ice is definitely being reinforced by positive feedbacks, but there are some negative feedbacks in that system as well, which are keeping it on a relatively kind of fairly predictable logistic curve downwards.
This reminds me, though, a few years ago I interviewed a scientist from Rice University, Pankaj Khanna, that was his name. Their team literally found broad steps of coral under the sea off Texas in the Gulf of Mexico. So for coral to die all at one level like that suggests the sea rose rather quickly, in steps, several times faster than the coral could adapt. So you've talked about in your paper something called the Labrador convection. What is that, and what does it tell us about the way tipping elements can unfold?
So the Labrador convection collapse that we talk about in the paper, it's a new element that we've introduced, and it's been branched off from something called the AMOC, the Atlantic Meridional Overturning Circulation. They have relatively similar drivers in that both of them are to do with where water flowing up the warm water flowing along the surface of the Atlantic flowing northwards, and then they sink both in the Labrador and Erminger seas in the north and northwest Atlantic, and then also off the northeast Atlantic as well, off of Greenland and Iceland. And both of those can be disrupted both by warming and also from meltwater flowing off Greenland as a result of that warming as well. And that changes the density of the water. It's sinking and it disrupts it. It makes it harder for it to sink. And at some point, it just switches off, both for the Labrador convection but also the AMOC as well. But the interesting thing we're finding in this study, looking at the literature, is that the Labrador and Erminger Sea convection can actually turn off a lot sooner than the rest of the AMOC. And it still has quite a big impact. It's not quite as big as the rest of the AMOC, but it still causes a huge amount of cooling around the North Atlantic region. It can disrupt weather patterns across Europe and North America, and it also can disrupt the monsoons in the tropics as well, in particular in West Africa. And perhaps most interesting is, for some listeners, is that it could add something like a foot to sea level along the eastern seaboard of the US and Canada, because it changes where some of that warm water is sloshing around in the North Atlantic. So it could go, sea levels could jump up a bit around those regions in only a decade or two.
But if I understood your paper correctly, you find that the Labrador tipping element and a related collapse of AMOC, as you discuss, could cool the Earth a bit, so not all tipping points lead to global warming?
That's right, although it's worth noting that's a temporary global cooling as well. It temporarily changes where heat is distributed around the planet. It changes where the radiators, some of the forcing is located, and it does lead to a global cooling in some of these studies. But it is a temporary thing, whereas some of the other things, like obviously releasing lots of carbon from permafrost, that carbon is going to stay in the atmosphere for thousands of years, so that's kind of a much longer-term concern. But yes, you could sort of see the AMOC and Labrador current as being kind of a temporary bonus that counteracts some global warming. But actually it causes a huge amount of weather disruption and chaos as well. So it's definitely not something that we would want to be experiencing.
And as you expand in this paper, not all tipping points are global. Tell us why regional impact tipping elements do matter. Yeah,
so we made this distinction in the paper. For example, if we're looking at something like the Greenland ice sheet collapse, that's a really big part of the Earth system that sort of pretty much goes in one big go, and it affects everywhere around the world. That would add something like 7 meters of sea level rise over thousands of years and cause some amount of global warming. So that's kind of obviously a global thing. Whereas some things like the loss of coral reefs, that's much more kind of each coral reef has its own localized tipping point, or similar with mountain glaciers as well. They're not obviously connected as one big unit that goes together. But what we're looking at is that a lot of these systems go at a similar level. So both with the coral reefs and the mountain glaciers, they go around about 1.5 degrees in our assessment, or 2 degrees for the mountain glaciers. And we're saying that the tipping in those systems might be localized to each glacier, to each coral reef, but they happen fairly synchronously across large areas of the world at a similar warming level. And also those systems have a massive impact on humanity, apart from the obvious thing of coral reefs and glaciers being kind of, it'll be tragic to lose them in themselves. They're of great value. Millions of people also depend on them. So coral reefs support hundreds of millions of people through fisheries, through coastal protection. Mountain glaciers provide drinking water to millions of people, hundreds of millions of people as well. So even though they're kind of not giant global units that sort of go in one fell swoop, they still happen over a similar time and affect millions of people. And that's why we designate them as regional impact tipping elements, so that they're still considered as part of that list.
Our recent guest, Michelle Dvorak, explained why her team concluded Earth will cross the 1.5 degree danger line before 2030. The UK Met Office suggests we may have 1 year at 1.5 in the next few years. In your new paper, when you talk about regional tipping points that could arrive with 1.5 degrees of warming, 3 are changes in the boreal forest. That is the vast band of trees circling the Arctic. What are the tipping elements there?
So the tipping elements in the boreal forest, in particular, there's the southern dieback, which is where there's, especially along the transition between boreal forest and steppe grasslands, you can get these fire feedback. So in particular around those regions, they're warming, they're drying out. That means that there are forest fires in the southern boreal forest. There's now much more likely to be the case that the forest will be replaced by steppe grasslands rather than regenerating as boreal forest. And then on the northern edge, we have actual expansion of boreal forest into what is currently tundra. And that matters because it's a lot of the tundra has permafrost underneath it. And so the expansion of boreal forest, which is darker coloured trees that has a different albedo, which means that actually it causes extra local warming. It boosts warming in those northern regions and helps warm up the permafrost underneath faster and the Arctic Ocean faster as well. We have those as becoming possible relatively soon, but the point at which they become likely we actually have is a bit higher up, kind of in the beyond 3 degrees sort of range. But that doesn't actually take account of things like deforestation as well, and there's a certain amount of uncertainty and low confidence on those ones. But it's certainly starting to kick in as well. And also in those regions, there's obviously permafrost, and especially abrupt permafrost fall is the one that's becoming already possible now and likely beyond 1.5 degrees. And that's where you get all these erosional features like overcast lakes and slope slumps and stuff like that help to boost greenhouse gas emissions and also really disrupt the landscape, destroying infrastructure like roads and houses and disrupting livelihoods in that part of the world.
New science finds the Arctic has already warmed 4 times faster than the rest of the planet. The Arctic is well past 1.5 degrees warmer than pre-industrial. Does that mean key tipping points may have already been crossed there?
So in our study, all of the thresholds we give are with respect to global temperature, the global mean surface temperature, and so do take account of the regional differences in warming as well, including that extra Arctic amplification. So we're not saying that we've crossed any tipping points for sure right now, but we are saying that they are possible at current levels of warming, even if warming were to stabilize right now, if emissions stopped right now, which of course is unlikely. We're saying that 5 tipping points are already possible, and several of those become likely beyond 1.5 degrees. So even accounting for that Arctic amplification within our global figures, we're still far too close to comfort, and we are of course heading towards 1.5 degrees pretty quickly.
Are tipping points reversible?
Mostly not. In our definition, we're focusing on self-sustaining change. Some previous definitions specify either being abrupt or irreversible, or both abrupt and irreversible. We're saying that they are often abrupt or irreversible, but not necessarily. There are some special cases where you could actually, at least mathematically, you can define a system that has some level of self-perpetuating, self-sustaining change beyond a threshold, but actually it could be reversible. And it's to do with this idea of hysteresis and biasability, whether or not you can get a system existing in 2 different states at the same, effectively, in this case, temperature level. That's not always theoretically the case here, but pretty much most of the things we're talking about are going to be irreversible changes, like the Greenland ice sheet. You can collapse that, and then at the same temperature, even if you got temperature levels back down to pre-industrial, you wouldn't regrow the Greenland ice sheet unless you actually went below pre-industrial levels. And that's a really good example of hysteresis and biasability, that you can't just easily reverse these things. You actually have to push far in the other direction to get a full recovery.
Check out the Radio Ecoshock website. We're at ecoshock.org.
You are tuned to Radio Ecoshock. I'm Alex Smith. Our guest is David McKay. He is a UK geoscientist and lead author of a startling new assessment about tipping points closing in on us as we heat the planet. David, a key chart in your new research article shows global core tipping elements. What qualifies as that?
So this is where we're looking at large areas of the planet that are covered by a particular system, like an ice sheet, an ocean current, or a rainforest. So they cover a large area. I think in the paper we define it as at least 1 million square kilometers. There's a tipping dynamic, a tipping process, which causes all of that to go in a relatively single process. And then also there has to be a certain level of global impact as well. So we're talking at least 0.1 degree added to global warming as an impact of that. And then that will obviously affect a huge amount of people, and in particular affects the whole state of the Earth system. So we talk about the Greenland ice sheet a lot. If we were to lose the Greenland ice sheet, and a lot of the other cryosphere elements around the Arctic, this would cease to be a bipolar ice planet, ice house planet. We've been in a bipolar ice house state since the last several million years. That's kind of a particular state of the Earth system that we're in. And if we were to lose the Greenland ice sheet and various other ice elements around that region, we would cease to be a bipolar ice house planet. We'd be a unipolar ice house planet. That sounds like a sort of, quite a sciencey textbook sort of definition, but it has really significant consequences for the planet. It would literally be a different planet.
7 out of the 10 global-scale tipping elements you look at warm the world even more. I wonder, are these warming numbers cumulative? For example, if the collapse of the Boreal permafrost happens and the Amazon rainforest dies off, do we add each number to whatever warming humans create by that time?
To an extent, yes, but there's some complications here in that these elements are actually interconnected to each other. And while most of them make other tipping elements more likely, some of them actually make other tipping elements less likely. So, for example, the collapse of the Labrador convection in the North Atlantic actually can protect the Greenland ice sheet to some extent because it causes regional cooling. And there are other examples like that. So it is technically, you could add up all those numbers together to arrive at some big final number. But in order to get a proper grip on this, you'd actually have to do some more complicated modeling where you feed all the different interrelationships between these tipping elements together and work out, if one goes, does it make the next one more likely at a particular temperature level? How much temperature does that add? You'd have to sort of crunch the numbers in a more detailed way. And that's actually something we're doing some follow-up modeling on using a simple model ourselves. And in general, yes, there is going to be some degree of amplification by these tipping elements, these tipping points being passed. But they do have some interesting interactions between them, which we don't really cover in this paper.
Well, that's what I was going to ask you. Does your study take into account the possible domino effect that Tim Lenton and his co-authors considered in 2008, how these tipping elements react with one another?
So no, not directly. All of the numbers in this paper are looking at the studies that focus on each of these elements on themselves, so that they're all individually assessed. So when there's when threshold numbers are given, that's just from the amount of warming necessary to trigger that element on its own. Obviously, the interactions are really important and could change some of these thresholds as well. But it was already a really big study as it was. So that's subject to some follow-up work. And I know that I'm working with some colleagues who are trying to work out some of the details of doing this interaction modeling to try and figure this out in more detail.
And just this year, eminent scientists like Michael Mann and Kevin Trenberth suggest Earth will stabilize at whatever temperature exists when humans stop emitting more greenhouse gases. They find the vast Pacific Ocean would mop up any continuing sources of heat, presumably even from the unfolding tipping points your group studied. But your work seems to point to continuing warming due to natural systems. What do you think, David McKay?
So in general, I tend to, especially if emissions were to stop now, the balance of evidence is that there would be relatively little extra warming. There was a thing called the Zero Emission Commitment Comparison Project, where they looked at this and found that overall models, as they sound now, suggest that emission stopping now would mean that warming would roughly stabilize. Some of them got a bit colder, some of them got a bit warmer. I think there's definitely a possibility of looking at that some of the models are perhaps underestimating we're seeing quite a lot of tropical carbon sink decline at the moment. That's possibly underrepresented in the models. So I think a precautionary approach would be to assume that maybe there would be, it would tend toward being a bit positive. There may be a bit more warming that will come after hitting zero emission commitment. But I don't think this paper, it doesn't directly undermine that sort of conclusion. There might be a bit extra locked in, but a lot of these things like the warming from Arctic sea ice decline or Greenland ice sheet collapse, things like that, some of these numbers are already included in the sort of IPCC warming projections. So they're not necessarily things you can directly add on top of what is already being projected. But I definitely think that in order to be on the safe side, we just should assume that there might be a little bit of extra warming in the pipeline, and that means that we really should cut carbon down as soon as possible.
Well, this new article in the journal Science continues more than a decade of study into tipping points, as we've talked about, and we can find that work at the Potsdam Institute, the Stockholm Resilience Center, University of Exeter's Global Systems Institute. David McKay, what brought you into this work?
So I've been interested in the linkage between climate and the biosphere for quite a while. So I started doing a PhD back in 2011 to 2015 at the University of Southampton, and I was studying paleoclimate change, so ancient climate changes, in particular looking at some periods of really intense climate change over the past 65 million years. And I was interested in how some of the longer-term feedbacks work between the climate and the biosphere, and also the ocean as well. I was working a lot with modeling of ocean and plankton and how carbon cycles between them. But that brought me more, I got more interested obviously in the current day and the sort of the possibilities of feedbacks now. And also from paleoclimate change, we can see that there are these periods of more abrupt change. You don't always see kind of gradual changes over time. Sometimes you see big step shifts. So that got me interested in the idea of tipping points, and also the idea that you might be able to use statistics on data to try and see if you can get early warning signals before these shifts happen. So I did a bit of work on, can we pick up some of these early warning signals from records before these ancient climate shifts. And so when I moved to Stockholm Resilience Center to do a postdoc with Johan Rockström, I was interested in kind of applying some of these ideas to the current day. So I've been looking at the biological pump in the ocean and how that might be affected by climate change. So the idea that plankton in the surface ocean, they export carbon from the surface, but they might not export quite as much in response to warming, and all the ecological complexities of trying to figure out exactly how that might change. So that's how I got into this area, and definitely you can see these feedbacks and tipping points being a big thing in the past, so it's interesting to try and work out, what does that mean for us now?
And this paper about triggering multiple climate tipping points got more mainstream press coverage than usual for science papers, but that will fade, we know that. We need a mechanism for such big scientific news and warnings to reach national leaders and investors and management and big corporations. Tell us about the University of Exeter Tipping Points Conference you just attended in September.
Yeah, so last week I was down in Exeter, and we were talking about both the sort of what we were terming as negative climate tipping points. We're looking at climate tipping risks, and also the possibility of kind of social ecological system cascades and breakdown and things like that. But we were also looking at the idea of whether positive societal tipping points can be triggered. The idea being that we're currently on a path to something like 2.6 degrees at least of warming on current policies, rather than the 1.5 degrees that would minimize climate tipping risks. And that's a huge gap to close. So maybe what we need is to trigger some sort of positive socioeconomic tipping points, that are like triggering social movements as an example of social change, or economic, something to do with technological changes that might help accelerate some of the transformations we need. So that was something we were talking about, and part of this is, it was proposed that there should be annual reports. So there might be one this year before the COP27 UN climate talks in Egypt. And the idea is that, the Global Systems Institute together with the Potsdam Institute might put together kind of a yearly annual report to kind of give the world an update on what the climate tipping point risks are, but also on what the potential kind of like the leverage and intervention points to trigger positive socioeconomic tipping points might be, and keeping track on all those things, looking for early warning signals, signs for destabilization, but also potential opportunities as well.
I'm really glad people are talking about this. We need to. Michelle Dvorak also told our listeners, even when humans get to net zero, warming will continue a bit, but only for a decade or so. She calls it overshoot. looking at your upcoming work, are you able to discuss your coming work on overshoot and the tipping points we just talked about today?
Yes, there's a preprint where a colleague of mine is looking at this idea of overshoots and climate tipping points. I can't talk about that too much because it's under submission rules of the journal, but the idea is, yes, what happens if we overshoot some of these climate tipping point thresholds, but then try and make a step back? What if we go over 1.5 degrees, maybe go up to something like 1.8 or even 2, and then bring things back down to 1.5 or below over time? Does that lock in some of these tipping point risks, or can we try and actually, can this minimize the risks somehow? In particular for some of the slower tipping elements, like the ice sheets, actually, the Greenland ice sheet and West Antarctic ice sheet, they have a sort of quite slow internal dynamics, which means that they might have to be above the tipping threshold we estimate for a number of decades before that collapse process really gets going. And so it's possible that if you manage to get warming back down within that time, it might be possible to, at the very least, slow down that collapse process or potentially avoid it entirely. But it's such an open area of research at the moment that we can't say for sure what the outcomes of that will be. So the precautionary thing to do is obviously just to cut emissions as fast as possible and try not to find out the hard way what happens when you pass some of these tipping points.
David, as we wrap up our time here together, is there a takeaway you want to leave with our listeners?
Yes, I think the main thing from this paper, there's two main things. I think this provides really strong scientific support for that Paris Agreement ambitious aim of 1.5 degrees, limiting warming to 1.5 degrees. Because originally that was more of a political goal. It was wrangled out by the small island developing states from the higher emitting countries who wanted originally there was a 2-degree target for UN climate negotiations, and 1.5 degrees was kind of, actually 2 degrees would be far too much for us, let's aim for 1.5. And originally that was kind of just an arbitrary number. What this does, this paper builds on growing evidence saying that, 1.5 degrees really matters. It is far better than 2 degrees, and there are various things that kick in around then which would really accelerate and deepen some of the negative climate impacts we're already seeing. So I'd say the first thing is this paper provides really strong scientific support for that having been a meaningful target. Of course, we are heading towards that quite rapidly and probably going to be going past it. So that it's a difficult message to say that 1.5 degrees is what we should be going for. But I would also say that even if we go past 1.5 degrees, even if we are going to trigger some of these climate tipping points, if we go beyond that point, that's not kind of a game over situation, because quite a few of the tipping points around about 1.5 degrees, the impact of those, at least in warming terms, isn't too big in the short term. They don't trigger a huge amount of short-term warming. And so that means that how much further we still go beyond 1.5 degrees is still going to be mostly up to how fast we cut emissions now. And that means we still have the capability to reduce the likelihood of hitting further climate tipping points, even if some of them are looking likely now. We can still try and stop other ones from being hit by cutting emissions as fast as we possibly can now.
Our guest from the UK is Dr. David Armstrong McKay. He lists himself as a geoscience resilience analyst, communicator, and advocate. He's the lead author of one of the biggest papers of the year. Exceeding 1.5 degrees C, global warming could trigger multiple climate tipping points. So the full paper is behind a paywall, but the authors have provided a clear, long abstract with a helpful global map, and that's free for everybody. Find links to all that and more in my weekly show blog at ecoshock.org. David, thank you for spending time with us here on Radio Ecoshock.
Thank you very much for having me on.
I'm Alex Smith. Actually, you as listeners can read this super important paper in full for free by going to David's website. Here is how. Go to davidarmstrongmckay.com. In the navigation bar, hover over Research to get the drop-down menu. Select Academic Publications. Scroll down to the Exceeding 1.5 Degrees paper. Click where you see Free OI Referral link in green. That takes you to a full read of the full paper in Science, courtesy of the author. And I'll put all these steps, of course, in my weekly show blog at ecoshock.org. It's worth it. You should read it. You can get right up to date with urgent action to avoid climate-wrecking tipping points. Go to climatetippingpoints.info for the latest. climatetippingpoints.info. I also recommend the website for the recent University of Exeter conference called Tipping Points: From Climate Crisis to Positive Transformation. The website for that is globaltippingpoints.org, with dashes between those words, Global Tipping Points. You can also find the link in my show blog at ecoshock.org, published Wednesdays.
You're listening to Ecoshock Radio for the world.
I'm Alex Smith. Get it all at our website, ecoshock.org.
This is Radio Ecoshock with your host, Alex Smith.
In September, methaneaction.org held a webinar on why we need to restore methane levels in the atmosphere. Former Earthbeat radio host and Methane Action CEO Daphne Washam introduces Rob Jackson.
Rob is a professor in Stanford's Earth Systems Science Department. He is the Michelle and Kevin Trenberth Professor and Senior Fellow at the Woods Institute for the Environment and at the Precourt Institute for Energy. Rob also chairs the Global Carbon Project, the premier academic institution tracking global greenhouse gas emissions. And with his free time, he serves on the board of Methane Action. So thanks for joining us, Rob.
Thank you, Daphne, and thank you all for your attention and for your interest in climate. I'll be talking about methane removal and mitigation. And I want to begin by saying that all of us involved in pursuing research in methane removal have spent our careers and our livelihoods really mitigating greenhouse gas emissions. In my group, we map street leaks of methane and look at appliances in homes and oil and gas wells. So we all know that mitigation is the first order of business. But as Dave mentioned, we've run out of time to simply mitigate, we believe, and want to pursue research into methane removal. And that's the focus of the talk that I'll be giving today, why that's important and how we might do that. Just to put a little flesh on the bones of methane rising, not only is methane rising faster relatively than carbon dioxide is, but the pace of increase is also going up. The increases in the last 2 years of 16 and 17 parts per billion were the biggest in the past 40 years, and we don't completely understand why that is. Probably methane sources are increasing, but sinks may be slowing so that the lifetime of methane in the atmosphere expands too. And that's one of the themes that I'll cover today. We need to think about reducing those sources and mitigating methane emissions, but also adjusting the sinks too. So methane's going up, it's going up even faster than it has before. So why methane? You've heard quite a bit about this already. It's very potent. In the last decade, methane was responsible for 2/3 as much warming as carbon dioxide. There are a lot of numbers for different global warming potentials. Congresswoman Pingree used 25. Sir David correctly mentioned that instantaneously it's more than 100. We had a paper out last year led by Sam Abernathy, a PhD student, and we believe that if the time frame of 1.5 degrees C is the goal that's important to you, then the valuation of methane should be at least 75. In other words, 1 ton of methane released causes 75 times the warming of carbon dioxide over the time frame between now and when we expect to reach 1.5 C increases, if that happens, heaven forbid. So it's very potent, and there's many good reasons to reduce it. For some justifications, it's the only lever at our disposal to reduce temperatures quickly, and by quickly I mean over a few decades, to reduce peak temperature thresholds and to delay them as well. And our estimates are that each billion tons of methane that's either mitigated or removed from the atmosphere will lower mean global temperatures by 0.2 degrees C. And importantly, and beneficially, will also reduce surface ozone by 1 parts per billion because methane as a hydrocarbon is involved in ozone formation. 1 ppb ozone reduction would improve crop yields around the world and would also save 50,000 lives a year, independent of the benefits for climate. So there are a lot of good reasons, both temperature-wise, climate-wise, and health-wise, for us to act quickly to address methane emissions. We can reduce methane in the atmosphere by mitigating it. So all of the arrows that are upwards in this figure are sources of methane to the atmosphere. The biggest two that we're familiar with are energy, fossil energy use, on the left, about 100 million tons a year, and agricultural activities, primarily cattle. The middle green arrow is the natural source of wetlands, the biggest in the world, of methane, which is the biggest natural source in the world. This is the arrow that we're worried about increasing with warming temperatures if, for instance, tropical wetland emissions go up or if the permafrost thaws. So not only do we have to worry about and be concerned about mitigating methane emissions from human activities, we have to consider scenarios where methane starts to be released from natural systems very quickly. But not only do we want to tackle sources, we want to tackle the downward arrows on the right. These are the sinks that are natural detergents for methane in the atmosphere and also soil microbes. All of these arrows provide options or arrows in our quiver, if you will. Let me take just a second to say, what is methane removal? Well, methane removal oxidizes methane in the atmosphere to carbon dioxide. You see that in the reaction shown here. Methane plus oxygen goes to carbon dioxide and water vapor. Methane removal mimics what happens naturally from natural detergents in the air. And it's important to realize that every molecule of methane that goes to the atmosphere turns into carbon dioxide over time. So obviously it would be better if we could turn methane into something that weren't a greenhouse gas. But by converting it to carbon dioxide, we are simply speeding the natural process. We can do this using catalysts or other methods I'll come to in a minute, and Renaud will discuss. Another important aspect to methane removal is there's no storage required as there is for carbon dioxide. We're not putting methane underground or anything like that. We're simply grabbing it in the atmosphere, oxidizing it, and releasing it again to speed up what nature does naturally. Some technologies that appear promising for methane removal. There are catalysts, both photocatalysts that use light, like titanium dioxide, metal catalysts embedded into high surface area frameworks like zeolites. There are aerosols or processes that enhance the chlorine and OH radicals that scrub methane from the air naturally. So you can think of generating these aerosols and releasing them into the air potentially to oxidize methane. And then we can do things to increase the activity of microbes in the soils as well, to speed up the natural sink that microbes provide. All of these things are in play and deserve research in our view. One last point I'd like to make is that research on methane removal will improve our ability to mitigate methane because most methane emissions in the world are at relatively low concentrations. They're above 2 parts per million, where the background concentration is, but below 2,000 parts per million. And the important thing to realize here is there's a technology gap. We have no mitigation capabilities now when the concentration of methane falls below 2,000 ppm. So if we can foster research to oxidize or remove methane at these low concentrations, yes, we want to be able to do that in the atmosphere, but we want to start at concentrations above atmospheric too. Coal mine gas that might be at 2,000 ppm, dairy gas that might be in the hundreds of ppms. So in other words, start with sources, what you would effectively call mitigation, and work our way down to true atmospheric removal. So there's an opportunity to improve mitigation by fostering and promoting methane removal research. Finally, I just want to leave you on a philosophical note. The UN just began its decade on ecosystem restoration. What is ecosystem restoration? Well, it's the process of assisting the recovery of an ecosystem that's been degraded, damaged, or destroyed. We have degraded, damaged, and destroyed aspects of the atmosphere, and I believe that restoration should be our goal for the atmosphere. And the only gas that anyone on this webinar could live to see restored to pre-industrial concentrations in their lifetime is methane, because of the combination of its short lifetime in the atmosphere of only a decade or so, and the fact that active and aggressive mitigation and removal could see it drop back to pre-industrial levels of, say, 700 parts per billion. That will be very difficult, and no one on this call believes it will be easy, but we want research to pursue that as a goal, and I think restoration is a wonderful framework to view healing of the atmosphere.
Daphne Weisham.
P.B. Barnard says, I'd love to hear the speaker's views on our chances of success in methane removal and climate restoration or repair more broadly if humanity does not also embark on an ambitious program of degrowing our global economy. Most of us know how our numbers and appetites are undermining all of our best efforts to solve our planetary and societal crisis.
Durwook Zelka, author and president of the Institute for Governments and Sustainable Development in Washington, D.C.
Okay, well, that's the kind of question that we need to go have a drink to answer. Let me give you a couple of thoughts on it. I mean, I think this is a profound question. Can we solve climate change in time in the current, capitalistic system that we now have? Or do we need a broader revolution of ideas? I think about that, but I don't work on that. I work on what we can do today, and it's a tremendous amount on the CO2 energy side, as everyone knows. We're doing remarkably well there. Now, the non-CO2 side, leading with methane, is the next piece. And we've moved that issue way up on the agenda for policymakers. Now we need to get the money for the research and the deployment. We need to follow the other advice from Sir David King on other restoration projects. I mean, there are other things to do with the Arctic sea ice, for example. I think we can do most of what we have to do in the current system, but I think about this broader question all the time. Do we really need a bigger revolution, which would have to be led by the young people? I mean, they say, paradigms, the old paradigms never die out, but the people who hold those paradigms do. And so there may come a moment when the young people do get to take over and we have a more just and equitable society where we don't have to fight as hard to keep the planet safe.
Rob Jackson.
We had a paper out a couple months ago just looking at relationships between human well-being and energy use. And the conclusion of that paper is that high energy consuming countries like here in the United States that consume 2 or 3 times the global average get very little for the extra energy that we use when you look at things like life expectancy, infant mortality, pollution, and sort of quality and length of life. We don't get a lot. And I think we have to have a discussion about demand side management. Reducing consumption of goods and changing diets is just as important as mitigating emissions. We can't just build our way out of the climate problem.
That was a selection from the online conference Methane Removal on the Critical Path to Reducing Peak Global Temperatures, as presented by methaneaction.org. Search that title on YouTube or find the link in my show blog at ecoshock.org.
Radio Ecoshock.
It sounds like Earth is heating up slowly, like 0.1.4 degrees per decade. But look at the record-smashing heat waves, drought, and floods in the summer of 2022, at least in the northern hemisphere. Our little measuring system doesn't really cut it. Maybe we should make every 1/10 of a degree into a full degree, like it matters. But scientists have a better way. It is called Earth Energy Imbalance. Here to explain is one of the world's top climate scientists, Dr. Kevin Trenberth. He is a distinguished scholar at NCAR, the U.S. National Center for Atmospheric Research, and an IPCC report leader. We will be working from Trenberth's new book, The Changing Flow of Energy Through the Climate System. From Auckland, New Zealand, Kevin Trenberth, welcome back to Radio Ecoshock.
Yes, hello, Alex. How are you? I should also mention that down here in Auckland, I'm affiliated with the University of Auckland.
Very good. Why that title for your book? What does it say?
Well, if you think about global climate change, the real problem is the human changes in the composition of the atmosphere. In particular, the buildup of carbon dioxide in the atmosphere. Carbon dioxide is built up by over 48% since pre-industrial times, since basically about the 1880s. And so the composition of the atmosphere is changing. Carbon dioxide is a greenhouse gas. There are some other important changes in other greenhouse gases, in particular methane and nitrous oxide, that are a result of all other human activities. The carbon dioxide results from burning of fossil fuels primarily. And a consequence is a changing in the heating of the system. And so we often refer to global warming, but warming is a synonym for heating, in fact, and it's much better thought of as global heating. And part of that heating goes into raising temperature, which is the other part that is a definition that's used for warming. It's ambiguous in that regard. But a lot of the heat doesn't just go into raising temperature. it goes into evaporating moisture, because over the oceans, 70% of the Earth is water. And so if there's extra heat available, the first thing that happens where it's wet over land or over the oceans is that water evaporates and puts more moisture into the atmosphere, which gets caught up in all of the weather systems. And as a result, the weather systems are more vigorous. It rains harder when it rains. This has consequences for floods. And in places where it's not raining, things dry out more quickly. And so the droughts are more intense, and we get heat waves and wildfires. And so these extremes that have come to the fore this year in particular, and have been widely publicized in the media in ways that have not occurred previously, are very much related to the increase in global heating. And so this relates then directly to the flow of energy through the climate system. In my book, I sort of set the stage for understanding more completely just what is going on and why.
You do indeed, and I love the book. I kept it by my bedside all summer and kept reading parts here and parts there. Let's dive into the real measure of climate change. Chapter 2 is called Earth's Energy Imbalance and Climate Change. You join other scientists to say energy imbalance is the key, but the idea has not caught on with the media or the public. What is this Earth energy imbalance?
So as I mentioned before, we have an increased blanket of greenhouse gases, the changing composition of the atmosphere. And so this interferes with the natural flow of energy through the climate system. So we always have the sun beating down on the planet, and it then gets involved in various interesting transforms, which is part of what the book is about, relating to how that energy from the form of radiation gets changed into what we call internal energy, which relates to temperature, and kinetic energy, which relates to movement, and potential energy, which relates to gravity and the height of the atmosphere or the ocean, or the depth of the ocean for that matter, and latent energy, which is the moisture content of the atmosphere, because when moisture condenses out, it releases the heat that went into it to evaporate that moisture in the first place. And it's all of these different forms of energy and how they get transformed from one to the other that gives rise to the complexity, and from a climate scientist standpoint, the interesting different ways in which this can be manifested in different parts of the world. And so the energy comes in, and then it eventually gets radiated back to space, but it gets radiated back to space at a longer wavelength, at infrared wavelengths. And so we can clearly separate out the incoming from the outgoing radiation, but the difference is the Earth's energy imbalance at the top of the atmosphere. And we can measure that from space to some extent. Now, we have satellites in space that are certainly measuring the components that are doing that, although we have to look at the more complete flow of energy in order to calibrate that fully, because it's very hard from space to get an exact measure, but we can get the relative measures. The changes over time we can measure very well. And so the energy imbalance is, on a global basis, about 0.9 watts per square meter over the globe. But 0.9 doesn't sound like much. And in fact, the incoming and the outgoing, net incoming and net outgoing, is about 240. So it's, 1 part in 250 or something like that. It's quite small from that standpoint. So you can't go outside and say, oh, I can feel the global warming. It's just it's just too small. But the trouble is that 0.9 watts per square meter averaged over the planet, the area of the planet is quite large. And so it ends up being about 500 terawatts. That's 500 with 12 zeros after it. And so then you start to think, whoa, that's a lot of energy. And, in my book, I describe some comparisons. The biggest power plants we have are maybe, of order 2,000 megawatts. 500 terawatts, the energy imbalance is about 500,000 of huge power plants, where we define a huge power plant as say, 100 megawatts. And so we've got 500,000 of these things adding energy around the planet every second, every day. For comparison, in 2018, the U.S. electricity consumption was about 0.5 terawatts, 0.5. And so it's, 500 versus 0.5. That's, a factor of 1,000. And, globally, the total energy consumption is estimated to about maybe 3.5 terawatts. And so, it's more than a factor of 100 in terms of the energy imbalance. And so that's why we'd sit up and take notice.
Isn't it amazing how the whole Earth system, from the bottom of the sea to the top of the sky, it was like a carefully balanced spinning top, or a carefully balanced state, and that was favorable to life as we know it. How far off balance are we now, and how is it possible that such a tiny thing, relatively, as human emissions from fossil fuels, could change the course of where oceans flow and cause ice to crack off and fall into the sea? These very big changes from what seems like a small addition.
Well, this has, of course, happened over time, except it has happened over millennia, over actually hundreds of thousands of years. And this is why we have the big ice ages in the past, things that we call glacials, where there's a lot of ice on the planet, and interglacials, times that have been quite warm, and the amount of ice is a lot less. And the changes there are related mainly to the changes in the orbit of the Earth around the Sun. And part of that is a redistribution, and part of it, the easiest way to think of it is that we have seasons. And, in the summer, we get a lot of sunshine, and the North Pole gets a lot of sunshine, for instance, in the summertime. But if we straighten up the tilt of the planet so that it just goes around and around, and it's autumn continuously, then the North Pole never gets any sunshine. And as a result, it cools. That's when it cools off. But if it gets a lot of sunshine in the summertime, then it melts all the ice and gets rid of it. And ice, of course, reflects the sunshine, and so that has a feedback effect. So rather small changes over a long period of time add up. And now what we're doing is changing the climate 100 times faster than anything that's happened in the past, in the geological past. So the numbers may seem quite small, but they are always in the same direction. There's a warming going on, and so they accumulate. And we can see that in multiple ways, and one of the best ways is actually through changes in the ocean.
It's interesting that we know the measurements of parts per million of carbon dioxide. The public and the media have kind of learned that. How many million parts did we reach this year? Richard Alley called CO2 Earth's thermostat. Is there a problem, though, with thinking of just carbon dioxide as a measure of our climate now and in the future?
Well, of course, it's not just carbon dioxide. Carbon dioxide is important because it has a very long lifetime. The stuff that we put in the atmosphere every day, as we breathe and carry out our various activities, drive cars and generate electricity and so on, some of that gets recycled quite quickly. It gets taken up in photosynthesis by trees, and we can look at that in the various records. One of the best records is at Mauna Loa, at the top of Mauna Loa in Hawaii, where they can measure uncontaminated by local cities the actual concentrations in the atmosphere. And so in the summer, in the spring and in the summer, there is a drawdown of carbon dioxide in the atmosphere as the greening of the northern hemisphere takes place. And then in the fall and the winter, as the leaves on the forest floor and twigs and downed trees and so on deteriorate, they put the carbon dioxide back into the atmosphere. And so there's quite a distinctive annual cycle of carbon dioxide. And the problem is that it doesn't get taken out of the system. And so the main way in which carbon dioxide gets taken out of the system is through the weathering of rocks, which is a very slow process, or it gets taken up in the oceans. It gets built into shells and bones of fish, and then when they die, they fall to the ocean floor, and they accumulate there and end up as a form of limestone. And there they are essentially taken out of the system. And so the key thing about carbon dioxide is its very long lifetime, that the stuff we put out there now accumulates, it builds up, although there's a strong annual cycle and even a daily cycle superimposed upon top of that. Other things, water vapor is very important. But water vapor has an average lifetime of only about 9 days before it gets caught up in weather systems. But, the changes in water vapor turn out to be very important in all of this as well.
That was Dr. Kevin Trenberth, Scholar Emeritus from NCAR, the U.S. National Center for Atmospheric Research. Kevin is now working with the University of Auckland as well, in his native New Zealand. Alex and Kevin are working from his new textbook on climate fundamentals for all of us, the changing flow of energy through the climate system.
We are totally out of time. I'm Alex. Thank you for listening and caring about our world.
Secretary-General of the United Nations Antonio Guterres addressing the 77th UN General Assembly on September 20, 2022.
Excellencies, there is another battle we must end, our suicidal war against nature. The climate crisis is the defining issue of our time, and it must be the first priority of every government and multilateral organization. And yet, climate action is being put on the back burner, despite overwhelming public support around the world. Global greenhouse gas emissions need to be slashed by 45% by 2030 to have any hope of reaching net zero emissions by 2050. And yet emissions are going up at record levels, on course to a 14% increase this decade. We have a rendezvous with climate disaster. I recently saw it with my own eyes in Pakistan, where 1/3 of the country is submerged by a monsoon on steroids. We see it everywhere. Planet Earth is a victim of scorched earth policies. The past year has brought us Europe's worst heat wave since the Middle Ages. Mega drought in China, the United States and beyond. Famine stalking the Horn of Africa. 1 million species at risk of extinction. No region is untouched. And we ain't seen nothing yet. The hottest summers of today may be the coolest summers of tomorrow. Once-in-a-lifetime climate shocks may soon become once-a-year events. And with every climate disaster, we know that women and girls are the most affected. The climate crisis is a case study in moral and economic injustice. The G20 emits 80% of all greenhouse gas emissions. But the poorest and most vulnerable, those who contributed least to this crisis, are bearing its most brutal impacts. Meanwhile, the fossil fuel industry is feasting on hundreds of billions of dollars in subsidies and windfall profits, while households' budgets shrink and our planet burns. Excellencies, let's tell it like it is. Our world is addicted to fossil fuels, and it's time for an intervention. We need to hold fossil fuel companies and their enablers to account. And that includes the banks, private equity, asset managers, and other financial institutions that continue to invest and underwrite carbon pollution. It includes the massive public relations machine raking in billions to shield the fossil fuel industry from scrutiny. Just as they did for the tobacco industry decades before, lobbyists and spin doctors have spewed harmful misinformation. Fossil fuel interests need to spend less time averting a PR disaster and more time averting a planetary one.
Radio Ecoshock.